Hello everyone, this is Mrs. McClelland, and this is my first attempt to create for you a video of the information in our course. So we're looking at Chapter 1, 1.3, Describing Quantitative Data with Numbers. You may notice that this is the PowerPoint that came with our textbook, however I have added some modifications, so you'll want to pay attention to those. So take a few seconds or minutes to take a look at the learning objectives that are in this section. I'm not going to go through them one by one because we are going to go through them in more detail. But these are the things that this section includes and what you will be responsible for knowing at the end of it. We're going to start with the mean. The mean is the most common measure of center, and we also can call the mean the average. You've been doing means and averages since sometime in elementary school, so I'm sure you're all familiar with how to find an average. Notice the symbolism X bar is used to indicate the mean of a set of observations. In the next slide you'll see that's a sample set of observations where we add the values together and divide by the number of observations. We use X1, X2, and so on to represent the individual data values in our set. So here's what our formula looks like, and we can also use the sigma notation, this Greek letter sigma, which is shorthand notation for add up the numbers. So we can rewrite this formula like this. It's a little bit shorter. X bar is equal to sigma xi, meaning x1 plus x2 plus x3 and so on up to n, divided by n, where n is the number of numbers. By the way, you may be interested to know while I'm doing this, I'm also making onion soup. On Friday night, I went with a group of my friends down to my church where we were making pickles, and we had lots and lots of leftover onions, so now I'm turning those onions into soup. So here's a picture of what my onions look like right now, and maybe I'll show you later how they're going to change as this time goes on. Okay, so important things to remember. This is what I added to the presentation. So the sample mean, X bar, is the mean of a sample and not the same thing as the mean of a population. We use the Greek letter mu to represent the mean of a population. Later on, I think it's chapter 7, we'll get a little bit more into that distinction. Another way to think of the mean is as a balance point of the data. If we were to split the data values up into equal size pieces, we would have the same number of pieces on each side of the mean. Think of it as like a seesaw. You can put half of the pieces on one side, half the pieces on the other side. I'm sure you're all also familiar with the median. The median is another common measure of center of data, and it describes the midpoint. So if you think about in geometry, if you have a line segment, the midpoint of the line is halfway through the line. That's the same thing as the median. If we line all of our data values up from smallest to largest, really disregarding the differences between the data values, we just put them from smallest to largest. The number in the middle is the median. Okay, so to find the median, arrange them from smallest to largest. If the number of observations is odd, the median is the center number. If the number is even, then the median is the average of the two center numbers. Hopefully in class we're going to take a look at each of these different possibilities so that you can see the difference in how to calculate one versus the other. Okay, so here we go. Here's a set of data. We're going to look at the set of data to calculate the mean and the median of commuting times of 20 randomly selected New York workers. These times are in minutes. So to find the average or the mean, we add up the numbers and we divide by 20 and we get 31.25 minutes. To find the median, a stem plot is very helpful. So we take the data, we put it in a stem plot, we put the leaves in order so that we have our data in the right order, and then we just count. So here in this case we have 20 workers, so we're going to count from either end to 10, and then the median is the sum of the 10th and the 11th numbers divided by 2. So in this case 22.5 minutes. Notice that no one actually has 22.5 minutes as their commuting time, but that is the median value. Okay, so here's just a couple of points about mean versus median. when a data set is symmetrical or roughly symmetrical, the mean and the median are going to be about the same. All right, so then you can use either one to represent the center. Many data sets are skewed. So think about baseball salaries, where most players make on the lower end of the spectrum, but relatively few stars make huge amounts of money. Or again, housing prices, where most houses tend to be in the lower range, but then there are those exceptions of the houses that are exorbitantly expensive, let's say. So here the higher outliers pull the mean towards the skewed end. So if you're adding in a number at the end, like 1 million or 2 or 10 million, it's going to pull those 200,000 or 300,000 up higher. Okay, the median, however, doesn't move. It's still the same middle number as it was before. So because of this, we say the mean is said to be not resistant to outliers, while the median is resistant. Let's talk about, so what is the mean and the median? The mean and the median tell us about where the middle of the data is, but they don't tell us anything about what the data looks like. They don't tell us anything about the spread. For example, San Francisco, California, and Springfield, Missouri both have the same mean annual temperature of 57 degrees Fahrenheit, yet they're very different in terms of their weather patterns throughout the year. I don't know if anybody's been to San Francisco, but it tends to stay probably between 40 degrees and 80 degrees most of the year, with some extreme examples outside of that. Whereas Springfield, Missouri is going to range from 0 degrees or below even, all the way up to 100, and yet they both have the same averages. So the measure of center can be misleading, or it's not really sufficient to give a good description of the data. So another description that is useful is called the interquartile range. And so let's see how that works. So to calculate the quartiles, the interquartile range, you first need to calculate the quartiles. The quartiles are easy to calculate. I think you've probably done this before. You find the median of your data set. Then you find the median of the left half of the data set, and that's called the first quartile. And then the third quartile is the median of the right data set. And your interquartile range, IQR, is defined as the difference between Q3 and Q1. It should be noted that, at least in this course, we do not include the median in the calculation of our first quartile and third quartile. I was never quite sure about that, but our book makes a point to point that out. Okay, so let's take a look at our New York data again. Here are our three numbers. We have our median is 22.5. The first Q1, the median of the first quartile is 15, and Q3 is 45. Okay. So let's see. Oh, wait a minute. I was wrong about that. Okay. So we're taking the average of the two 15s, which is 15, and then we're taking the average of 40 and 45, which is 42.5. So the IQR is the difference, 27.5 minutes. Okay, so how do we interpret this? We say that the middle half of all the travel times, from the first 25% to the 75% margin, is 27.5 minutes. Now, outliers. We've talked about outliers. We've talked about potential outliers. Now we have a rule for interpreting outliers, and it looks like this. We take 1.5 times the IQR. Notice that the IQR is a number. We multiply 1.5 times that number, and that gives us our boundary for outliers. So now what we want to do is we take the Q1 is 15, and Q3 is 42.5. IQR is 27.5. So for these datas, we take 1.5 times 27.5 gives us 41.25. So Q1 minus 1.5 times the IQR is negative 26.25. So we're not going to have any outliers on the left side. And Q3 plus 1.5 times the IQR is 83.75. So any data value more than 83.75 would be considered an outlier. So let's take a look at our data again. And we have an 85. So the 85 would be considered an outlier. Now, the last thing we want to look at for this video is the 5-number summary. The 5-number summary includes the minimum value in a data set and the maximum value in a data set, as well as the 3 values we've already been talking about, the Q1, the median, and Q3. So the 5-number summary gives us a quick look at both the center and the spread, and also tells us a little bit about the shape of the distribution, whether or not it's skewed to one side versus the other. And in our next lesson, we're going to learn how to take this data and create a box and whisker chart. So anyway, this is the end of this video, with the exception of, here is my soup. It's not quite finished yet, but it's going to simmer for a while, and then we're going to make it into delicious French onion soup. I hope you've enjoyed this, and I will see you soon.